Howdy guys, we're going to talk about the mole and it's going to be awesome where you want to be on this page of your notes. So without further ado, we're going to move on to that first part, which is the pure substance and the mixture. You need to know the difference between the two. So a pure substance is something that's uniform completely through. So that's either going to be an element or a compound. You guys should know what those are for now, but the element is on the periodic table. The compound is when it's chemically bonded, okay? So it's chemically combined. That is going to be your big IB term right there. So for a mixture, it's just a combination that is not chemically bonded. So a homogeneous solution is uniform throughout, and that is going to be a solution, like an aqueous solution, is always going to be homogeneous. Something like brass or rubber, something like that is going to be homogeneous. Now, heterogeneous is not uniform, and you can come up with 100 different examples of those. So, a good particle diagram of these four. Now, you can see if you really pause and examine, and you really try to point out the differences, you can obviously tell that this is heterogeneous because it's not uniform throughout. You have clumps right here that aren't evenly distributed. Now here, these are evenly distributed, at least somewhat. Now that's the best we can do. Now for a compound, now this one is also evenly distributed. So what is really the difference between this one and this one? You have to look closely because these are bonded together. A green one and a purple one are bonded. So that is the real key. All right. So let's get into the periodic table. All right. We're going to talk about a little bit of geography here about your entire periodic table that you will have. Please keep one ready. Download one on your phone. Keep a paper copy. I don't care. Just look it up, Google it, whatever. All right. So they're organized by groups and periods. There are 18 groups and only 7 periods. Groups go up and down, and then periods go left and right. Now this is the periodic table found in your data booklet, and this is the one periodic table you could have on all 3 papers, all 3 exams, in every exam that you take in my class. Now, so we have the alkali metals, the alkaline earth metals, the transition metals. Now note that zinc is not a transition metal. That's why it's got a circle on it. It's got not a transition metal because it has a full set of d electrons, and so it doesn't qualify. These are known as the representative elements. Then they have different names, so nobody really quizzes on that. These are the halogens, and those will be important later, and the noble gases. These have different names called the intertransition or the rare earth metals. Now you should be able to know this. You should already know that the left side is the metals, the right side is the nonmetals, and the staircase in the middle separates the two. Anything touching the staircase, except for aluminum, is going to be a metalloid. Now these have different properties than metals and nonmetals. Metals are typically hard, brittle, and they're solid. Nonmetals are typically gaseous or liquid. But non-metalloids can be kind of in the middle. Metalloids also have kind of a cool property of being superconductors sometimes when they are very cool, very cold. So one cool thing, that's why we use silicon. All right. Now some people ask me why is an astatine one? It's because nobody really cares about it that much. Poor astatine. All right. And these are unnamed. IB still calls them unnamed, but they are named. And nobody really knows much about these. Okay. So another way to look at it is the electron configurations. Remember that this is the S block, right? This is that D block. This is the P block. And this is the F block. Now, something's different about this one. Helium is on the other side, right? Because helium is actually part of the 1s2 electron configuration. All right, so Sometimes you actually do see helium on the other side on different periodic tables. A couple other periodic tables you have in your data booklet are ones, just so you know that they're there, that arrange them by melting points and boiling points. So melting points on top and boiling points. That'll be good for periodic trends when we look at those later in the year. First ionization energy, electron affinity, and electronegativity. These are all in your data booklet available to you during free response tests, okay? Not during multiple choice. You won't need to know these numbers in multiple choice tests. And then atomic and ionic radii for these. So this is kind of gives you a scope of what information you have available. This is all in your data booklet. All right. So let's move on to the kinetic molecular theory of solids, liquids, and gases. First of all, the solids are closely packed. They're more ordered than both liquids and gases, and the particles are always in constant motion, but they just kind of wiggle in space. All right, they have translational motion. They cannot switch places with another one around it. So this one cannot switch places with this one, right? That's what I mean. So they have no flow, they're not compressible, and they have a fixed shape and a fixed volume. Now liquids are they're still closely packed, but they're more ordered than gases. That's an entropy term. The particles are always in constant motion. All right. So what happens is the liquids they have more energy than solids, so they're able to move around, and they do have translational motion, which means that they will be able to move in between. And I'll show you a moving picture later. Well, they have flow, and they're not easily compressible. Most people don't get that one right there. So now the gases. The gases have have 5 points to their kinetic molecular theory, and this is for an ideal gas. Now remember that an ideal gas is perfect and never exists. It only exists on paper, but it is what we assume about gases. We say that they're so small that they occupy no space at all. They're teeny tiny. The particles themselves don't actually occupy space. It's the space in between that is what is making up all that space. The particles of the gas are in constant motion and move in straight lines until a collision occurs. A collision between gas particles and between gas particles in the walls of the container are perfectly elastic, which means that they do not lose energy, okay, when they collide with each other. There are no forces of attraction. Now remember this one, because this one is going to contradict in a little bit. And then the average kinetic energy of the particles of a gas is directly proportional to the Kelvin temperature of the gas. All right. So if kinetic energy goes up, the Kelvin temperature goes up, the absolute temperature. So this is what gases look like. Now you can see we can draw them in a particle view with lots of space in between. It's obviously not to scale, but you can notice that the length of this vector right here is much longer than the length of this vector, right? Or the magnitude of this vector. So, or the magnitude of this one. They move at different speeds, and they move in straight lines until they collide with something, and then they with an inelastic collision, they just bounce right off. Okay. Now they have flow and they are compressible. Now you also need to know about aqueous solutions. It's not actually a formal state of matter, but it is important to understand that the solute solvent mixture can be thought of as a liquid in terms of particle motion. Okay, so think of it as a liquid. It's not a formal state of matter, but it is a homogeneous mixture. You'll need to write all four of those, solid, liquid, gas, aqueous, when you write chemical equations, you need to be able to do that. So when we change state, you must know all 6 of these. You must know that moving from a solid to a liquid is melting. Now the liquid to a solid is called solidification or freezing. They will accept freezing. Liquid to a gas is evaporation or vaporization. And then gas to a liquid is called condensation. And you also need to know sublimation and deposition. So a lot of people are working on those two as well. So make sure you work on them. All right, we'll do balancing reactions later. All right, so let me just show you a simulation here of neon, of some 4 gases, and this is of a solid, liquid, and gas. Now these are actually in motion. I want you to pay very close attention to the intermolecular forces. That is the forces of attraction between molecule and molecule. All right. So we have neon, we have argon, we have oxygen, and notice oxygen is diatomic right here, and water. Now, big change with water. That's because water has extremely strong intermolecular forces. Water is special. It has hydrogen bonding. Okay, always remember that. So now those were as a solid because they're closely packed. They're not moving. They can only wiggle in space. Now as a liquid, they can move around and even spontaneously evaporate, like here. They're not cooperating. And as argon, oxygen, that's something a little different with that one, right? Maybe it has a little more attraction of forces, right? So maybe it would have different chemical properties, which may be different boiling points, different freezing points, all right? Those intermolecular forces have to do with that. The IB wants you to understand that. Now for water, another good one. So you may have been noticing the temperature changes right here. So let's try one more time with gases. So here we go. That's what a gas looks like. You can see them bouncing around, and they behave pretty much like an ideal gas, pretty close. Argon also behaves pretty close to an ideal gas. But we get to oxygen, and we get some weird things going on. Watch it go. Now see if you can see one thing that contradicts. You guessed it, I gave a hint earlier. It's the attraction of forces that you see going on right here. Those things actually really are happening, and those are things to consider when you're looking at real gases. So again, the attraction of forces, the intermolecular forces, is a huge deal, especially in IB chemistry. So be prepared for that. Now the intermolecular forces here of water. Now water is moving so fast that they still don't have much time to bond, but they still have forces of attraction, as you see. All right, that's going to be it, guys. Have a great day.